So a formal welcome to everybody joining us tonight. We've got three speakers with us tonight, Richard, Stuart and Brandon. And I'll give their proper introductions as they come along. The first speaker is Richard. Dr. Richard Hall is Vice Chair and represents the UK in the International Energy Agency Solar Heating and Cooling Technology Collaboration Programme. He leads energy transitions work in the solar governance. Richard currently chairs the Solar Trade Association and the Solar Heat Working Group. So Richard, welcome, and the floor is yours.
Hello. Okay, let me see if I can share this screen with you. Is that working?
Yes.
Perfect. Yeah, hi. So, I'm not spend too long introducing myself. So yeah, so I'm Richard. I do a bunch of stuff around solar governance. So, the sort of the rules around the solar energy industry. And I thought I'd give a little talk today about the rise and fall of solar thermal in the UK, because I think it's sort of an interesting story, and it's really important that you know about it. So let's continue. So this is really about the real reasons why solar thermal declined in the UK. So not the sort of the not so real reasons. And it is a work in progress. So yeah, we some of these ideas are sort of new. I haven't really talked to anyone about before, and some of them are sort of well known. So yeah, do comment, and hopefully you'll engage a bit of discussion later. This all started because we had the BEIS consultation called the Future Support for Low Carbon Heat. And essentially, it sort of suggested that the government was going to end support for solar thermal. And there were a couple of reasons in there, but one of the reasons was deployment of solar thermal has remained low. So I thought that was kind of interesting. I mean, is it true or is it false that solar thermal has remained low? So we can have a look at the deployment data. So the deployment data is just how much of the technology you deploy. And so here is the deployment data. I think you can see my mouse pointer, hopefully. Essentially, along the bottom is the years, and essentially along the other axis is the amount of solar that's deployed. So you can see here that we had a sort of rise until 2010, and then we had this sort of huge fall off. So when they say solar deployment has remained low, it's actually unfortunately been falling for a number of years now. And what I want to talk to you about is about why that happened. Because if you look at other countries in the world, so here's a plot of all the countries that sort of we monitor as part of the Solar Heat Worldwide work. The UK is right on the right. And then if you look at the countries like here, so you look at sort of Denmark or Austria or Germany, for sort of very similar countries, it's not, Spain or Portugal or something, but they have way, way higher solar thermal deployment than us, like significantly higher. And I think this is, and why is that? People, you could say, is it more sunny in Denmark than the UK? Obviously it's a silly thing to say. It doesn't make any sense. So why does it happen? And that's what I want to go through. So let's take away and let's try and I think I got this timeline right, but let me know if I got something wrong here. I'm sure I probably have somewhere. But essentially we had a low carbon building program, which was a sort of grant-based scheme, and you got some money towards it. And then actually it was 2018 with that the RHI was suggested and put into law. And then it was actually only in 2014 when the RHI started. So there was this sort of like strange sort of period between this low carbon building program, and then we had this renewable heat payment scheme, and then we had this sort of renewable heat incentive, and you just see there's this whole sort of it just continued to fall. So that it didn't fall because of the RHI, it was already sort of in that process. So I think that's a sort of important part to bring up. So what happened? And I want to talk firstly about the solar shock. So in April 2010, the feed-in tariff came in. And this was for solar photovoltaics. And the price was set at about 50p. And I think it was about 55p for retrofit. And it was like 40, 50p for new build, something like that. But this was a huge value. So there's this huge shock to the system in 2010. And remember, in 2010, you're between these two schemes and people are thinking about the renewable heat incentive and things like that. And so, yeah, in here, so you have this sort of solar shock in 2010 happening. And what I tried to do here, if you can see it, it's a sort of definitely the work in progress part. So along the bottom is the net present value of the system. And along the top is the deployment rate. So like how many systems are being deployed, and you can apply it to like countries or states. And essentially what you should find is that the better the net present value, the more deployment you get. And so the little red markers are solar thermal, the little blue one or air source heat pumps, and the orange markers are solar PV. And you see that initial point where there's this huge net present value, and the deployment could have been so much higher, but this is probably, the first year, and really, it's probably constrained by just the sheer number of the number of installers that were available at the time. But you can see that the value proposition just economically was so much better than all the heat technologies. And I'll go into later sort of in why that is, and there are reasons sort of why that is. And you can see on the little graph in the top, basically, solar thermal and SOSP, don't even, you can barely even see them on the graph compared to solar PV installations. So I think that sort of tells you quite a lot. So what could solar thermal have done? This happened, and the answer really was to get cheaper. So the sort of good news for solar thermal is that it really did get cheaper. So over the last 10 years, we have evidence to say that solar thermal did get cheaper. So essentially, this is a graph showing the installed price to the consumer and the cumulative installed capacity. So when you plot the two, you get, how much cheaper is it getting every time you do an installation. So that's called like an experience rate. And both, so the top two ones are solar thermal and solar PV, and you can see really both technologies have a really high experience rate. Whereas, the air source heat pump and ground source heat pump and biomass at the bottom really struggle. So I think that's sort of, it's interesting. So great, that's really good. So the industry did work to get cheaper. This is really, fantastic. And it did really work hard to get cheaper. But this was sort of the problem. So solar thermal had some other challenges, and these were really structural and really difficult to overcome. They weren't so easy. And so I'm going to go through a couple of them that I think are important. I think there's a couple more that I can think of, but I'm going to try and just do some of the main ones, I think. So the taps and baths only policy. So solar thermal deployment was limited to doing taps only. And I think this was like due to the SAP 2012 and the fact that it's still in use. So if you go to the SAP, which is the standard assessment procedure for residential buildings, you see the Appendix H, there's only a calculation for solar thermal for domestic hot water. And as far as I understand, there's no way to get that into the space heating demand. So you really are super limited to one element. And to give like an analogy, so imagine the situation where heat pumps could only be used for bathrooms. Imagine there was a law that said you can only use heat pumps for bathrooms, or imagine where there was a law saying you could only use PV to power your television and nothing else. You had to connect it directly to your television and you couldn't do anything else. And that's kind of what happened with solar thermal. So it had this sort of like this real challenge to overcome. And as far as I understand, it's sort of still in place. And then the problem there is that the domestic hot water is on the more expensive end of solar thermal. So as with anything, the bigger it becomes, the cheaper it gets. So in 2018, we did this research for Denmark that basically look at the different costs, the different type of systems. And essentially, definitely domestic hot water is more expensive than the combi. So if you can do space heating and hot water, it gets cheaper. But the regulations didn't really allow that. So we were stuck in this zone on the left, where Denmark and everywhere else was going to these really, really low cost options on the right. And we're sort of still stuck in this sort of, domestic hot water, which is still a great use for it. But you could definitely have seen sort of cost reductions if you allow these sort of bigger systems to come to play. And to sort of quantify that into some sort of, EPC improvement. So I don't know if EPCs are like the rating level for the cost of energy in a house. And so got SAP 2012 and SAP 10.1. And essentially with SAP 2012, you just get stuck. You get stuck, you can't go anywhere. So you can't, unlike other systems where if you make it bigger, you get more energy out of it, and therefore you get more EPC points. But when you're limited to domestic hot water only, you get in this sort of stuck position where you can't really go anywhere. So hopefully that illustrates that. So that was one issue. Next issue, cheap gas. So in the UK, gas is, relatively cheap, or the prices of gas are relatively low. And this is really encourages the use of gas for central heating. So I pulled this off Eurostat just the other day. So you can see, I've tried to draw a line where the UK is. And you see the UK gas price, the gas prices for domestic customers are really on the very much the low end of the whole of Europe. And you can see by the amount of gas that's used in the UK, most people use gas boilers. And if you look at countries that have high numbers of solar thermal and heat pumps and low carbon heating, the sort of Denmark and Sweden territory, it's not hard to draw a sort of correlation between the gas price and the prevalence of, say, heat pumps and solar thermal. And you always get, and this is a well-known thing, so it's not, every year you get people, saying like our gas prices are too cheap, and essentially this came out the other day. Literally, like I saw this, I think it was like 2 days ago. Essentially, they're looking at heat pumps for London, and they're saying, and there's only like 300 installations of heat pumps on the RHI in London. And basically, one of the reasons they said was the rebalancing of electricity and gas prices. So, and I could have picked at anyone. This is the Carbon Trust, but it's sort of a general, everyone knows this is the case. And every year you see something related to rebalancing of gas and electricity prices. So yeah, low gas prices are a real difficulty. That's compared to, say, if you're replacing electricity. So that's why in the off-grid, so where, situations where you don't have access to the gas grid, solar thermals are just the fantastic option. It's a really, really, really fantastic option because you don't have that, really difficult competition to deal with. So next one is the static grid. So I don't know. I mean, it's probably like, definitely, I'm not a SAP assessor or anything like that, so don't get me wrong. But I mean, as far as I can figure out, and yeah, please do correct me, but as that you in the SAP 2012, you're still using the carbon emission factors for 2012, which, always, I'm not sure whether I'm right in there. So essentially, Carbon Brief did this great article about a year ago, 2 years ago, about the trajectory of the power sector. And essentially since 2012, the power sector has decarbonized hugely. It's less than half of what it was in 10 years. And yet, I think, you look, I mean, I just opened up, the latest, SAP on the website, and the carbon emission factors are still there for 2012. And then I looked, and the Ground Source Heat Pump Association say this as well. So, they look at this and say it's not great. So in August 2018, the vice chair of the Ground Source Heat Pump Association at the time said the carbon factors in SAP are not great, and essentially people are working with these really old numbers, and they don't really reflect the true situation. And then they said, the damage has been to the heat pump industry, and I think probably I don't know, he's probably correct. You know, if the SAP emission factors were quite different, then you might see some very different changes to the sort of the structure of the low carbon, heating sector. So yeah, so the emission factors are a big one, I think. But the other one is combis everywhere. So, or I like to say the tank apocalypse. So, these modern combination boilers, it's a fantastic innovation. Like, absolutely, don't get me wrong. If it's a very sophisticated product. But essentially, as far as I understand, like all of them don't need tanks. So they don't need a tank. They instantly heat your hot water, and they've really dominated the market, probably because they are so good. And so if you look at the sort of the structure of the gas market, you can see that these combi boilers now make up 50%. So you can think about, that's 50% of the market that has forgotten about tanks and have used the space that used to have a tank for something else. And so that's a real challenge to the solar thermal industry, because for the most part, you need, a hot water tank. And the Solar Blogger did a great article in 2014 talking about the rise of the combi boiler and the implications of that. And essentially, the conclusion that Stuart made, or the Solar Blogger made, was that combining solar with combi boilers was left in the too hard box. And I'd question whether enough effort was made at the time, or even now, to really get some fantastic solutions for combining combi boilers and solar thermal, and how to do that. I don't know. I'd be really interested to know whether there are great solutions to that, or whether it is still legitimately a challenge.
5 minutes.
So I think, thank you. So I mean, there are lots of reasons about hassle and red tape. So I think scheme design is an art, and the schemes need to work for the consumers, installers, and manufacturers. They need to work for everybody, really, and they're very difficult things to do. And the RHI, was known to be not very good. So this is a paper from 2016, just really highlighting that the RHI wasn't really, trying to explain that it wasn't really working. They compared the results to the feed-in tariff with the RHI, and were just basically saying that, I think I remember saying it was like they're meant to be 10 million CHP units in people's houses by, the prediction of the RHI, and the numbers are just so different. But essentially, they said the hassle factors between the scheme design and the actual implementation just had a really big impact on adoption rate. So, that's a super big, important aspect to get absolutely right. And, the question is enough attention made to the scheme design to make it, really smooth, and the transition between two schemes as smooth as possible. And, it's questioned whether we do that right. And then I think finally, if I've got enough time, the one more brochure fallacy. So there's this focus on marketing over dealing with some of the hard structural problems. So, solar thermal, the idea that, it's great to do brochures, and, these are two excellent brochures, which are really good. And don't get me wrong, like we produced this one for Solar Heat on Cities, and it's very nice, and Solar Thermal Now by the SEDA, and they're two really great brochures. But I think and I think given the opportunity, the public loves solar. So given the opportunity, people will buy solar. But I think dealing with the structural problems is really important. And this idea that, it's probably just a problem that something that people say, just if we marketed it a bit harder, everything will be fine. If we marketed it a bit better, everything will sort itself out. But actually, I think, and this is a paper from 1984, sort of saying the same thing. But I think the energy sector is a bit like a game, and the game has very specific rules, and the rise and fall of energy technologies is a large degree a result of the performance within the game. And to win the game, you have to really engage with the code and change the mechanics. And I think, you know, there's one thing doing the marketing, but I think also there needs to be this huge emphasis on understanding the rules of the game and making sure the rules of the game are correct, so that it makes it so easy for people to choose solar thermal. So here's my list of some of the things which I think is really challenging. So the shock, the taps and baths, the cheap gas, the static grid, the tank apocalypse, the hassle and the red tape of the schemes, and maybe too much of an emphasis on marketing over actual dealing with the structural challenges. So if I had sort of one message from this presentation, it was, you know, focus on structural change, you know, focus on those things. And I think the deployment will just flow once that's done. So is there hope? Final slide. Yeah, so there's loads of hope. So SAP 10.1 is coming along, and that includes space heating. So that's a huge barrier that's going to get removed. It also has more realistic emission factors, so that should be a big improvement. Heat pumps hopefully are going to start increasing deployment, and both solar PV and solar thermal work great with heat pumps. So absolutely, you know, more heat pumps is definitely a positive thing for solar. And also the gas levy. So there's some talk about increasing the gas prices, and more rational gas prices is probably going to see more solar come along. So yeah, hopefully that's 20 minutes. There you go. Thank you very much. That's the end of my slides.
Thank you very much, Richard. That's great. I'd like to welcome Stuart next. Stuart Speak is the founder and CEO of Sotropy, and he set up the company to develop this idea of an ice immune solar thermal panel. So he has an engineering degree from Robert Gordon University, and over the last 30 years has worked in various areas and disciplines. Prior to Sotropy, Stuart worked for 20 years for W.L. Gore, the makers of Gore-Tex, where he led a multinational team that successfully implemented new manufacturing IT systems in the Gore's Japanese factory. He's the winner of the Made in Scotland Inventor of the Year 2018 award, and that's for the Ice Immune Solar Thermal panel. And I know personally he's done a lot of research in order to get Sotropy on the ground, and for that research, I have invited him to speak to us tonight about his research on the panels themselves. So without further ado, Stuart.
Thank you. Thanks, Chloe. Right, I'll just share my screen. There we go. Okay. Yeah, there we go. Yeah, thanks for that intro. I'm not going to be talking about my panels today, though, you'll be pleased to know. And I don't know if I'm going to be talking much about all the different technologies out there, because when I started doing the presentation, really, there's only two real sort of mainstream solar types of thermal panel, basically flat plate and evacuated tube. But just to go back a step, I don't know who's all out there. So what is solar thermal panels, or what are solar thermal panels? It's a really simple technology in principle. Energy from the sun hits an absorber and heats a fluid. That fluid is then used to heat water some way. It's actually the most efficient of the sort of renewable technologies, because it is so simple. It's basically heat to heat. So this is showing you a basic representation of what a system would look like. And this is only 4 taps and baths, as Richard mentioned, because systems are basically limited in the UK now, from the point of view that you don't get any subsidies if you do space heating, but it is entirely possible to do that. Solar thermal panels, they're basically heat to heat, and they're the most efficient of the renewable technologies. The mainstream technologies, you have a flat plate, which is what is here. It's basically a glazed insulated box with a black absorber on it. And there's pipes thermally connected to the plate, which you run the fluid through that you want to heat, and the energy is transferred to that fluid and then goes to a water cylinder or storage. They can be roof mounted, they can be integrated, and they come in set sizes. So, you'll get ones which are a certain size. The other type is evacuated tubes. So an evacuated tube is basically, it's a glass tube with a vacuum in it. It's the same technology that is a thermos flask. So the thermos flask was invented in whatever 1800 and blah de blah. It's basically two tubes within a tube, or a tube within a tube, and there's a vacuum between the tube. There's also another type of evacuated tube, which is a slightly higher efficiency, and that's the whole inside of the tube is evacuated. And the reason you have that vacuum there is because it's the best insulator in the world. These tubes typically, even in Scotland, internally can get up to maybe 200 degrees C. In other countries, Dubai, hot countries, or sunnier countries, they'll get up to 220 degrees C inside that tube. You can still touch the outside of the evacuated tube because the insulation is so good. Efficiency is round about up to 80%, and that's the same essentially for flat plates. There's a range from maybe 50 up to about 80% efficiency, which sounds great, and it is great when you compare that with the likes of PV panels, so photovoltaic panels, which produce electricity. You're lucky if you get 20% out of them. So you can see they're an order of magnitude better at capturing the sun's energy, but it converts it to heat. It's not electricity. If you need electricity, obviously PV is better. So, but it's not all about efficiency. When you're designing a system, you could have a system which is, 80% efficient, all the energy's there, but if it costs $1 million or £1 million, it's, it's going to have a payback of thousands of years. So when a system is designed, the capital outlay is obviously very important at the beginning, because that will affect, how much payback you're going to get, and it has to be reasonable. You can't have it beyond the lifetime of the system, I would say. Okay. So system design is paramount, and things which are critical in system design is, how big is your hot water storage? So generally speaking, if you have a larger hot water storage, then you have a larger amount of water where you can store the energy, and it tends to be, the system overall tends to be more efficient. Other limiting factors, though, are things like if you have a system which has antifreeze in it. So in the UK and most of Northern Europe, solar thermal panels have to have antifreeze in them. And the reason for that is if they freeze in winter, it would damage the system, it would burst. But the thing when you use antifreeze is that you can't overheat antifreeze. So you have to actually design the system so that essentially it doesn't overheat. And that essentially means the sunniest day of the year matched the amount of storage you have in the system. That limits the size of the system essentially to what you can balance between the amount of solar panels that you have and the amount of storage. So for example, if you had in the UK, you have 4 square meters, you probably need round about a 200 litre hot water storage, so that on the sunniest day of the year it won't overheat. But then demand also comes in, so demand profile also comes in. So if you're taking that energy away all the time, then you can probably have a bigger system. So it's another thing which is very important, the demand profile. If you have antifreeze in the system and capital outlay. So the most important thing really is, it's not the efficiency of the system, the panel itself, it's the overall system efficiency. And that's called the solar fraction, is how much energy you're actually getting from the sun, you're actually using. It's usable energy. And it's one of those things that, you have to balance it so that it comes into the system design and system modeling. Aesthetics also come in. So some people just don't like the look of, you know, the tubes. Some people don't like the look of the panels. One of the nice things about flat panels, they can be integrated into a roof. The main, you know, the main market out there, potential market out there, is actually for retrofit. So you're not going to be ripping off tiles to put a solar panel in anyway. System robustness, so that also means things like, you know, if a pump fails, what happens? So on a system with antifreeze in it, potentially you could degrade your antifreeze, and then you'd have to get a technician round to purge the system and refill it. You can get away with it a few times, but over time it will degrade. And then there's the maintenance aspect of it. Antifreeze requires basically every 3 to 5 years, it should really be replaced. So all of these other things come into it. It's not just about efficiency. So Kingspan probably had one of the most efficient solar thermal panels using evacuated tubes on the market. They recently pulled out, and one of the reasons, I'm pretty sure, in my opinion, is that the high cost of the system meant that the capital outlay was high. That coupled with, you know, what I've talked about, you know, the robust system robustness. So the maintenance does come into it. So what does a solar thermal system look like in a little bit more detail? So this is what a typical one would look like. You have the solar thermal panel on the left, top left. You have a shared tank with a boiler. So in this case, it's a gas boiler. And I agree completely with what Richard was saying earlier. Gas is so cheap that if you're competing against it strictly on a you know, payback, then it can sometimes be really difficult, especially on small systems. So this is showing what a typical system is, and you can see there's not a lot to it compared with a PV system, where you've got more complicated electronics with inverters, you've got wiring. Essentially, all you've got is a controller for your to tell this pump when to pump, and you set it so that if the temperature at the bottom of the tank is lower than the temperature of the panel, then pump and start transferring that energy to the tank. So what I thought I would do is I would take this system and I would do some scenarios for you just to show you how really the efficiency doesn't really come into it that much. What I did was I took a flat plate with an efficiency of about 75%. Kingspan's evacuated tube system, again, that was about 77%. And I took an evacuated twin wall system with 60%. So you can see what this has done is this percentage down the side is how much energy is actually usable energy to the system. And you can see that for the three systems, they're all round about the same in this design that I did. Round about the 40% mark for the overall for the year, and you can see quite clearly how it changes throughout the year. So you're up at 65% here in summer, or April, May, June, July, which is pretty good. And then it tapers off, and that's purely because there's less sun. You can't magic up the sun. But this is the interesting thing, between the lowest and the highest, it's only 300 kilowatts of difference. So in this simulation that I've done, so that's about 15 pounds for the whole year in gas or electricity, which has gone through a heat pump. So heat pumps basically reduce the cost of the energy by 3 roughly, which means 15 pounds. So if it was a straight electric through boiler, for example, it would be about 45 pounds. So your efficiencies are not that important. So that's going from 60% up to 77% efficiencies, around about 17% different. But the most important thing is it's actually how much energy you can use, and that's where these other things came into it. So Sorry. So the other thing that I thought we'd do is just to show you what it would look like on a space and hot water system. So this is showing a low energy building being heated by an air source heat pump down on the left, bottom left, solar thermal, a tank or a cylinder of 600 litres of water, underfloor heating over here, and hot water demand. So don't worry about all these other bits involved. Basically, that's showing you. And what I did again, I did the three types of solar panel. So what we have here is, sorry, it keeps in. Right, sorry. So again, you can see here that overall, because there's more energy being used, the overall solar fraction, how much energy the solar is providing, has gone down a bit because you're using more energy for the heating. But again, up here is the actual solar fraction. So the first one, which is the flat plate, and that's got an efficiency of 75%. If you go by the stats in the EN key mark, 23.5% is the solar fraction, 27% for the Kingspan, and 25 for the 60% twin-walled one. Not a huge amount of difference. And you can see here it's broken it up. How much of that is for the hot water? Again, so Kingspan's coming out slightly better, 51. Solar fraction to the whole of the building is about 10%. So this design here, I didn't. This design, I didn't spend a whole lot of time, making it more efficient. I've run ones where we actually can get, something like maybe 30% solar fraction for the whole of the system for a house. But that's just to give you an indication of what it's not all about efficiency. It's all about good system design. It's about energy demand. Yeah. So I don't know how long that's been. How am I doing? How long have I got, Gloria?
Just over 5 minutes. Yeah.
Okay. So just as an aside, I had this slide. It showed quite nicely what 25 meters of solar thermal will look like. And I just want to, a lot of people say, yeah, you should be using solar PV for heat. Now, I guess if you've got solar PV installed and you want to get rid of that solar PV energy because you're not using it, then yeah, do it. But if you are serious about getting heat and decarbonising heat, then solar thermal is definitely the way to go about it. So that's what 25 meters squared of solar thermal will look like. I've done some modelling with this sort of amount and coupled with an air source heat pump. And you are getting something like maybe 40%, 30 to 40% of the total energy requirements of the house from solar thermal. If you wanted to do the same with PV, this is what you would need to get the same amount of energy. And it's a very similar graph for solar PV. It's basically what the sun can provide. And I think you'll agree it's not practical in a lot of cases if you want to do it. So that was quicker than what I actually thought. So this is basically our system. We have a modular system there on the left. And we also have, it can freeze without damage. And the beauty of that is that you can use water in the system and you can allow it to freeze. But the knock-on effect is actually that you can allow for bigger systems and start to eat into the space heating market. And right now, you can't really do that for the domestic market. You can do it for the office market. We've just actually got a large R&D grant from the government to look at this in more detail, and hopefully we can come up with a really good case for it, so we can start seeing solar thermal actually help to decarbonize. And I think that's all I've got. Yeah.
Thank you very much, Stuart. That's very insightful into the actual panels themselves. We'll probably ask you more questions about the ice immune part of the things and how that improves the system and all that sort of stuff at Q&A. For now, I'd like to introduce Brandon. That is, if I find the right document to put in front of me. This is a great one, isn't it? It just disappeared. Brandon is actually come from, well, not come from New Zealand, but he has joined us from New Zealand because he had an accidental emigration.
Yeah.
Due to COVID. So very interesting circumstances. And he's now started working as a heating engineer over in New Zealand. But before that, Brandon has an interest in energy since late 90s, being partner of the Solar Wind Energy Development Cooperative. He studied at University of East London for his MSc in Advanced Energy and Environmental Studies, though he originally trained as a shipwright, moved to timber frame restorations, barn conversions, and then low energy housing. Since 2005, he has been installing solar thermal, pellet boilers, and ground source heat pumps. He bought out a plumbing and heating company located in Mid Wales in 2008 and has since been working within the rural off-gas grid heating industry, specializing in linking up renewable energy systems, including biomass and air source heat pump installs. So over to you, Brandon.
Okay, bear with me. I'm not technologically very able, so I'm going to try and make this work for you all. Good morning. For me, it's currently 6 in the morning. Why does this not come on? Hang on. There we go. Can you?
Yes, great.
Can you see it? Can you see what you should see, or can you see what I'm seeing?
We can see your screen and the slides. Well, we can see the PowerPoint.
Oh, here we go. There we go. That looks about right to me.
Yeah, that's great.
So as I say, yeah, good evening to you all. Good morning from New Zealand. I'm adequately caffeinated. That's why I got to go last, so that I could wake up and get on with it. I was asked to speak a little bit about the real world situations and about how we actually go about this. I'm no theorist, that's for sure. I've never really got down with reading and writing, but I'm very much a hands-on guy. I've always been fixing things. So as it says there, in the real world, well, what are the realities? What actually works and what actually doesn't? So this is something I grabbed quickly from boilerguide.co.uk. I thought typically people would probably search online. So I searched what is a solar thermal heating system, and this is what came up. I thought the interesting bit is the bit that I've put bigger down at the bottom of the screen there, that I've increased the font on. And it says this solar heated water can supply both a wet central heating system as well as your taps, baths and showers. And yet very seldom is that what we see, as has been spoken to both by Richard and by Stuart. Actually, the RHI, the system under which most installs are done presently, explicitly do not allow that to happen. It's just for taps and for baths, as has been said. So I thought that was quite an interesting thing from a website that comes up at the top of the list, and yet that's not the reality that we actually see. So why are we here? This has been touched on, which is great. I like the fact that you two guys have already spoken to this. So we had government schemes. These were incentives to induce people to take up renewable technologies. We had the Clear Skies system that started back in 2003, I believe it was, as part of the low carbon building program. And we had the RHI, which was promised for 2011 and didn't come in until 2014. And during that period, Richard mentioned we had the PPI, which is Renewable Heat Promise Payments Incentive, if I recall correctly. So this is where all these restrictions started. And there was some influence from other parts of the industry that kind of meant that the systems we had were very prescriptive, and they were just for domestic hot water. There were a couple of outliers in the field, but they were very far and few between. The difference with the Clear Skies, it was just an upfront grant. I think it was £300 towards the installation, whereas the RHI now does a quarterly payment for 7 years in a domestic setting, and that's on your deemed carbon savings of the system. There are other issues involved there with how one would calculate them, and as Richard was talking again about the way the SAP calculates it and what it allows us to do. So there are certainly issues in there. So what can we do to make this better? Now, my personal interest comes from energy, and I'm interested in using energy as sensibly as possible, as cleanly as possible, and as efficiently as possible. So what I look to do is I look to offset any kind of fuel, be that oil, gas, electric, wood, whatever it might be, with solar. That's my main aim, is to use as much solar and as little as other as possible. So as I see it, we have the two options that are usually used in the UK. We've got domestic hot water, the traditional reserve of solar thermal. This has been spoken to already several times during this meeting. That's kind of the normative thing. We have a hot water cylinder, which is heated from a solar panel. It comes up to 60 degrees C, and then it's switched off. Then we have all the problems of stagnation that get involved, the limited energy use that we can actually benefit from because we have such a limited system. And as Stuart just said, you know, the issues of having very low energy gain in the winter and an excess of heat to deal with in the summer, and just, yeah, all sorts of good things to play with. The other one is the heating contribution. This is really what I've been doing now. I should probably put it out there that I don't think, I was racking my brains, I think I might have done one microgeneration scheme, which is the MCS in the UK. And in order to get that, you have to be RHI compliant. They kind of go hand in hand. I think I've probably only ever done one that complied because it only did hot water. Generally, most of my systems have always been related to the heating and therefore just not eligible for any grants, which shows that some of my clients have got the right idea. But anyway, so what this enables us to do is to use lower temperatures in the winter. So in the winter, often you can find that solar panels will produce heat, but it might not be enough heat to satisfy domestic hot water demand because we can't get the hot water hot enough. However, that can be put in as a direct kilowatt hour replacement into a heating system. In the winter, we have a large demand for kilowatt hours. There's just a large energy demand, and we can provide some of that, by no means all of it, but by some of it. And this enables us to offset whatever other fuel might be used with genuinely, I believe, clean and free energy from the sun. So how can we do this? How does this actually work using it for space heating? From a design point, a hydronic design point, there's no real reason why modern houses and even retrofits can't be heated with a lower flow temperature than we typically use. An awful lot of heating systems are working at 65, 70, 75, even 80 degree flow temperatures. I hate to break it to you, but that's not at all necessary. We can do this at far lower temperatures. So we can do it 35 to 40 degrees C. A good friend of mine, a chap called Stephen Calvert now, he's based down in West Wales, sorry, you'd kill me if I said Mid Wales, down in West Wales, and he does not design his heating systems with a flow temperature above 35 degrees Celsius. It's perfectly doable and we can make it happen. So there are considerations that we need to bring in, there are things we need to think about. Primarily our emitters, so that would be our radiators or our wet coils, our fan coils if we're using those, our underfloor heating. They need to be correctly designed and specified. And in order to do this, we have to have an accurate heat loss calculation done. We need to know actually how much heat we need and where we need it in order that we can deliver it correctly into the building. An awful lot of heating design, unfortunately, is still done by rule of thumb. Richard touched earlier on the combi curse, as I would call it. He called it the tank apocalypse. I quite like that. And this is a thing whereby people put in bigger and bigger combination units, combination boilers, because it's easy. And the problem is that in order to provide hot water directly and instantly, we have to have a fairly large output. So it's not uncommon to see 24, 30 or even 40 kilowatt combi boilers on the wall. And they're then trying to do the heating as well. And so a lot of calculations gone out of the window because people just throw them in. There's plenty of power. You'll always get the heat you need, not necessarily very efficiently. So the way we tend to do it is to integrate it. We take the solar and we take other sources, whatever they might be. Being rural, a lot of what we do involves log boilers or biomass boilers. We put that into a buffer tank from where we can draw the heat. And this is being seen more commonly now with heat pumps, especially with air source heat pumps, is you'll see a buffer tank in an installation as well as a cylinder. I differentiate between a buffer tank and a thermal store. A thermal store would provide your hot water indirectly through an instant hot water coil, whereas a buffer tank wouldn't provide hot water directly. You typically have a cylinder beside it. And again, every kilowatt hour from solar directly displaces a kilowatt hour from any other fuel. And as I said, our heating demand or our hot water demand can be drawn from that tank. Just as a note, it's really odd presenting with absolutely no feedback. I'd kind of like you all to have your microphones on so I can hear you, but maybe that's not the way we do it. Yeah, it's a bit odd. I'm used to being in front of people, not a screen. So what do we need? What do we actually require? What do I, as an installer, require from you, either as a client or an architect, to be able to do this? How big is it? How vast does the system need to be? Is it large and cumbersome? In a word, yes and no. It can be either. As far as the roof space goes, typically we would start with a 30 tube panel, for example. I'd use on a fairly typical house, and that's about 4 meters by 2 meters by the time we've got our entrances for our pipes into the roof and that sort of thing. The panel itself is a bit smaller, but we need about that much space. Now, of course, these come in multiples. Typically we use 10, 15, 20, 30 tube units. They're modular. We can use as many or as few as we like. Obviously, the greater the area that we have upon the roof, the more energy is available, the greater potential we have. And you can have as much as you want. And we did one where we had 80 square meters of flat plate mounted on a hillside. And no, you carry on, chap. You want some? Yeah, I'll have some toast. Sorry, my boss has just come in and he's offering me toast for breakfast, which is quite nice. So yeah, we have done huge ones, and that's like that had a 5,000 litre store on it, and that provided domestic hot water and heating for a pair of holiday cottages and a farmhouse, and that worked jolly well. Typically, the issue comes an awful lot where we need space to put this stuff in, and of course, the curse of the combi boiler or the tank apocalypse means an awful lot of places no longer have an airing cupboard. Whilst we have retrofitted whole systems into a traditional airing cupboard, it can be a little bit tight. And if we can increase that area to 1 meter square, then it's amazing what we can fit in with a bit of ingenuity. So a full height cupboard of about 1 meter square can do a domestic house. And typically we'll be looking at somewhere around about 300 litre cylinder to be able to do that. This can be located anywhere. We've done them in lofts, we've done them in basements, and we've done them on any floor in between. The only thing I would ask is if you're designing it or specifying it, that you would think about the fact we have to get pipes to and from there to the roof, obviously for the solar, and then everywhere else to distribute for it. This is a little example, the first one bringing up. We can see here on the left, you've got two 20 tube arrays. This is actually my brother's house up in Lancaster. I did for him because I'm nice like that. So he has a thermal store that you can see on the right there. That's a vented thermal store. It runs the solar on a coil in this instance. I've subsequently changed the way I tend to do that. I tend to go direct. It's got a small wood burner into it as well, a little 5 kilowatt wood burner. He also has an old Potterton Puma combi boiler, simply because it's perfectly functional. Didn't work very well on the hot water delivery, but it was perfectly functional as a boiler. And we changed it into what we refer to as a system boiler. And that goes directly into the tank as well. And from there, we take hot water and we take his radiators and his underfloor heating. Just a former council house, nothing fancy, built in the 30s. It's been re-rendered, as you can probably see, and we put a couple of bedrooms, extra bedrooms on the side. But it's a fairly standard install for us, that one. So how can we make this work? How do we actually, it's all well and good saying we can do it, but how do we make it work? Now, on this, to me, it all comes down to control, both the controller getting the energy in and then distributing the energy back out again. And that can make or break a system. The amount of systems I go to that have basically cooked and died because there was very little control on them, or they've been poorly designed on the control thing is, yeah, the list is very long, and I've got lots of horror photos. Depending on what's being used, as far as the kit, we may have to implement third-party controls. There are some very good built-in controls. I think of some of the heat pumps we use now, they have some fantastic controls in which we can also control the solar and all the heating zones as well. But typically we find ourselves doing something that's a little bit more bespoke, and therefore we need third-party controls on it. One of the biggest tools we have available to us, this is in order to allow us to use the solar for the heating, is weather compensation. Now, for those who don't know, weather compensation varies the flow temperature to the heating system, to the emitters, in relation to the outdoor temperature. So take my house as an example, well, one I'm just selling back in the UK. On a design day at minus 3.7 degrees Celsius, it has a heat load of 4.94 kilowatts. Let's call it 5 to round it up. Now, anything above minus 3.7 degrees Celsius, that heat load reduces. so I don't have to throw 5 kilowatts at it. And it's a fairly basic graph that allows us to see what's happening. So what we can do with the weather compensation, I can heat my house with a flow temperature of 40 degrees Celsius because it's designed for such, at minus 3.7 degrees externally. So as the heat load reduces, so is the requirement of energy that needs to be delivered. I can do this one of two ways. Either I can reduce the flow rate so I can deliver less water at the same temperature, or I can reduce the water temperature and deliver the same volume. That delivers me less energy. So what this means is that the temperature that I need to heat my house is actually less, and therefore I can use a lower temperature water or lower grade heat, as we would call it, which solar is perfect for delivering. This is another example that we did. This is in Llangadvan in Powys. As you can see there, thank you very much. He's got 45 tubes. I was talking about modular panels. I would have gone for 40, but the guy liked the symmetry of 45, so it's absolutely fine. He has a 400-litre vented thermal store. You can see on the right-hand photo there, it's a small cupboard, this one. It actually comes through a little access hatch that the store was put in and the cupboard is built around it. But it stands 2.1 meters high, and the store itself is 600 millimeters in diameter, and then we have our gubbins around it. Just as a point of interest, something that Richard said earlier with his combi comment, there's a little yellow valve in there. I don't know if you can see it, 3 little yellow knobs. That's a thing called an what do they call it? A solar combi valve or something made by Intertech. That's a valve that we use quite a lot when there is an existing combination boiler. And basically what it does is if there's heat available, it always draws the heat from the thermal store for the hot water, domestic hot water. If there's heat enough available, it sends it directly to the taps. If there isn't, it will draw in a feed from the combi boiler as well and blend it in to a safe temperature. So it acts as a diverting valve, a blending valve, and a heat uplift valve, which is a very useful thing. Now, that little valve I've just circled with the red there, that's the weather compensating valve. Well, it's a 3-port proportional rotary blending valve, but we're using for weather compensation. That's the one that allows us to decide the temperature we want to draw out from the tank and deliver to the heating. This is another one we did. Abercegir is a slightly different scale now. It's a brand new house. That's Gareth Daniels there, world champion shearer, as it happens. And you can see on the left there, he's got an east-west facing panel. So he's got 30 tubes facing each way. That's why we have 2 pump stations. He has a 1,000-litre thermal store and a 20-kilowatt biomass boiler. Now, in the summer, he doesn't use his boiler at all. He just uses a solar thermal. In the shoulders of the season, so spring and the autumn, he's primarily using solar. Occasionally, he might light the boiler. But all his domestic hot water and all his underfloor heating and radiators come from that store there. It was a brand new house we built. Well, we didn't build, I was involved with. He's a farmer, he has plenty of wood, and that's what he chose to go with. Again, you can see there's our valve that does our magic. There's actually a 4-port valve for those of you who want to geek out on such things. But yes, it's exactly the same technology being used again there. Ultimately, we actually swapped it, and you can see we put another 1,000 litres of storage in because he decided to use a wood kiln. So he had a wood kiln just as an afterthought connected to it because he's a joiner as well. And we put in an extra 1,000 litres just to give him extra capacity to be able to run the kiln, all working off the same system. We just kept putting more storage in so he can run his boiler a bit harder. And that's how it goes. This is an example I didn't install from another chap called Ross Mackenzie up in Aberdeenshire. And I figured given the geographic nature of this Zoom meeting, or at least where it's being hosted, this might be of interest to you. So here we can see Ross has got 3 flat panels in. He's running a 500-litre store, sealed store. And just of interest here is this is his Wii controller. And you can see that the weather at the time, this was just a couple of days ago, actually, he took this from me. So this is on the 6th of October at 11 in the morning. And yeah, it was cloudy weather. This wasn't a clear day by any means. Look at the external temperature, 11.6 degrees. And yet we can see that his solar panels are at 51 degrees. That's the temperature being delivered to his store at the time. His whole system runs with a flow temperature of 45 degrees Celsius. So at this point in the Highlands in Scotland, he's quite happily heating his house with solar. This is stuff we really can do. It's not rocket science. Why am I interested in low temp? This is, to me, this is where the 2 things that I do come together, the heating aspect and the solar aspect. As I said earlier, the lower the heating water temperature, the greater percentage of it I can provide from solar thermal. Even on grey days, I can still get solar in my panels. The rule of thumb I used to say to people is that actually when you look out of the sky, I'm looking at now, and it's completely vile out in New Zealand, so I hope you got nice weather in the UK. If you can see where the sun is through the clouds, i.e. you can see its location, albeit not blinding you, then you get reasonable solar gain. On the days where it's completely overcast and you can't tell, then there really isn't a great deal to be had at all. But most of the time, there is some gain to be had. It may only get your panels to 35 or 40 degrees Celsius. And now that would not do domestic hot water, but it is still temperature that we can use. The trouble is very often, if you're just purely running a domestic hot water situation, your tank might be at nearly that temperature anyway, and therefore you get no gain, you get no energy capture at all. Whereas if we're running a heating system at that temperature, we can draw down from a buffer and we can keep topping it up. The trick is to keep your temperatures as low as you can, because your buffer, the lower your buffer temperature or cylinder temperature, the more gain we can get from the panels. And a lot of people struggle with that concept, but it's pretty basic. So as I said earlier, if I can heat my house with 40-degree flow temperature at minus 3.7 degrees C, then even at that temperature, I can use what's coming off the solar panels if it's sat at 40 degrees C. Anything above this is an external temperature, and my required flow temperature, because my weather compensation, drops. And therefore, it's just a win-win. It gets easier and easier to be able to provide the heating we require, or at least a percentage of it, from the sun. So I guess that comes down to, is solar thermal the panacea that we've all been waiting for? And in a word, no, it's not. I'm really sorry to have to tell you that. But every kilowatt hour that we can harvest from the sun is 1 kilowatt hour that's saved or displaced from another fuel. And that really is where I've always come from, is the fact that anything that we can offset, anything that I don't have to pay for, it doesn't have to be delivered down a pipe or doesn't involve me splitting another log, to me is a winning situation to be in. Low temperature heating systems allow us to make the most of any solar thermal potential that we have. And I believe it to be a genuinely clean and free energy. It's decentralized and it's readily available. Is it universally applicable? In retrofit, yeah, maybe, sometimes not. It does depend rather on what's being done and what's going on in the house. In what would be called a refurb, yes, I'd say unequivocally, it ought to be. And in new build, I genuinely believe it should be mandated. The fact that we're allowed to put up houses that have a 40 kilowatt combi boiler in them, which probably only have a 6 or 7 kilowatt heat load, I find to be an absolute fallacy, frankly. And one of the things
is need time.
Okay, this is my last. I'm here.
Amazing talk. I forgot to warn you for time. Sorry.
Okay, so just on the pitfalls on installation, glycol, which has been touched on particularly by Stuart, we have issues with it cooking. It overcooks and it ruins systems. Leaks. My experience is most systems are plumbed by people who are inexperienced and don't really know how to do it, and we end up with leaks on the stainless pipes. Poor workmanship is something that I see an awful lot of, which leads to terrible systems. And education, I think, needs to be increased. But that's somewhat beyond the scope of this talk. Yeah, just photos of what we see all the time. But that's basically what I have for you, Glo. So hopefully that'll do.
That is wonderful and remarkably on time.
Oh.
Thank you, everybody. And it's a really great 3 speakers we've had there. I hope you all agree with me. I will attempt to share my screen and show you. I had a very good question from Jacqueline earlier about the net carbon contribution, so manufacturing of the panels and delivery and all that, and how we balance that with the energy saved. And yes, so life cycle analysis definitely is on the cards. What I want to show you is the next 2 talks we've got coming up, which is, I hope you can see now, 11th of November. And we've got basically the theme of the PVs, so as opposed to tonight. And on the 9th, oh, wrong button. Oh, if it'll work on the 9th of December. We are going to talk about passive use of solar, so solar sun spaces, and also in co-housing schemes, and how we could merge the different solar technologies together with Hockerton housing, which has been done more than 10 years now. I can't remember the exact year, but it's been very well POE'd, post-occupancy evaluated, and one of their engineers and person living there, Simon, is going to talk to us. Oh, I've got the name wrong there. And we've got the giant in solar architecture, Beat Kampfen, from Zurich, to come and speak to us on the same night, and how he managed to design in solar in almost all his projects, I believe. So these are only the first 3 of a longer series that is yet to come. We will be talking about maintenance and user issues, like in social housing, for example, commissioning of systems and batteries, and controls and all sorts of things. So if you do have other topics you would like to hear, please do put it in the chat. I'll save the chat before we end, and make sure that the topics you'd like to hear about will be arranged into a talk. So without further ado, I'd like to open the ground to Q&A. For that, I will stop the recording.